Hello, good evening, everybody. My name is Malvin Matthew, and I want to welcome you to your CIVE615 or MEM678 non-destructive evaluation class. I'm a PhD student that graduated from under Dr. Antonius Consos. Most of my work has been with using image processing and computer vision for infrastructure damage assessment. And you will quickly realize how much image processing and computer vision is actually being used with infrastructural, damage assessment at the end of the day. So with that, I'm going to start off on the lecture. If you guys do have any questions, feel free to ask Dr. Consos or even like email me. My email address is mdm, that is Mike Delta Mike, 359@drexel.edu. All right, with that, I'm going to stop my video and hopefully share my screen so we can record the video. All right. I'm hoping you guys can hear me while I'm doing this. All right. So this lecture we have been giving as part of Dr. Antonius Consos' lab, which is the Theoretical and Applied Mechanics group, which is up here. It was initially presented by a colleague of mine, Dr. Andrew Ellenberg, who now works with Lockheed Martin. And since I have edited a little bit, just like give you guys a little bit better understanding, right? So with that, the presentation is basically going to contain the outline, which includes the introduction, the image processing techniques and measurement. These are broadly classified, and I'm going to break into a little bit more of depth within each one of these, right? So first of all, what is image processing and how is that different from using Photoshop, right? So one of the major differences is that image processing can use multiple different techniques to produce whatever we define as a desired output, and that definition for desired output depends on the user, right? But essentially, once you have that, that technique can be used for more than one image. And the desired goal is in finding out different characteristics within that image. Now, then the next question would be, what is the difference between image processing and computer vision? Therein, we realize that image processing is basically just the brunt work of identifying features within the image. Computer vision is essentially classified as using intelligence to understand what is within that image or what has been derived by image processing. So it is somewhat of a blurry line between the two of them, but essentially image processing is a fundamental part of computer vision. Computer vision does not have to be a fundamental part of image processing, right? Now with that, we walk into some of the fundamentals, which is what is a digital image? Now, for all intents and purposes, as far as your computer is concerned, or as far as your Python code or your MATLAB code is concerned, a digital image is just a matrix of numbers, where each pixel, which is each element of this matrix, has a value associated with an intensity value or a color. Now, with regular images, there are the standard RGB, which is the red, green, blue, or grayscale. So how RGB works is essentially there are three different layers of matrices, each with different intensity values for those colors that are overlaid on each other to give you that full final picture. But generally, when we're doing image processing, we do tend to use grayscale images alone. But again, this varies from application to application depending on the user, right? Now, there are different color spectrums outside of RGB, which is basically the HSV color space, which goes to hue, saturation, and value, as you can see right here. And then there's another one that's just called YCBCR color space, which is luma, blue difference, and red difference. And we break into a little bit more of these as we go through the lecture as well. Outside of just the color spaces, we also should understand that each one of these images contains within itself coordinate systems, right? So you have the world coordinates, where basically wherever your camera is taken, wherever your camera is imaging from, And then the image that you're taking gets registered onto your camera sensor plane. And we're going to break into this when we go through the pinhole camera model. But realize that there are 3 different coordinate systems within the image itself. So there's the image XY, which is also given with the UV for the pixel location, the camera coordinates, the XC, YC, ZC, and then the world coordinates, which is XW, YW, Z. This is just generic fundamental information that you need to know. This especially comes into use when you're trying to measure something by taking images of it in the real world, right? Now, there are various camera parameters. Some of the inputs that you use and which you have seen would be the ISO, shutter speed, focal length, aperture, target distance. And all of that eventually affects the brightness, determines the minimum and maximum distance, the scene pixel size, which is basically how much of your real world distance is your camera covering in pixels, and then the amount of noise. Breaking into a little bit more of these, a little bit more depth of these, let's start with aperture, which especially when it comes to measuring things within a field of view, the aperture becomes very important because of this factor called the depth of field, which basically means that as my aperture reduces, so such as f/16, a lot more of my image comes into focus. Whereas if my aperture is much larger, not that much of my image comes into focus, and there's only a very specific zone that comes into focus. Another one obviously is the focal length. As this diagram indicates, the shorter the focal length, it has a larger field of view with a larger depth of field. And as your focal length gets longer, you have a narrower field of view and a narrower depth of field. So this is what a 14mm camera's lens is going to look at on a camera. And that same image with a 600mm lens is going to look like that. Fun fact, the human eye generally perceives sight at around 50mm, well, as though it's capturing images with a 50mm lens. Another aspect is shutter speed. So obviously, you need to be slow in darker places, but fast is better for high speeds in the image. So a slow shutter speed is going to give you a lot more motion blur, whereas a fast shutter speed will take immediate motion. But however, because how quick the sensor is actually exposed to the light, you're going to have lesser light coming into the sensor. So it's going to be a darker image. So you're going to have to vary these factors as well. Another well-known camera parameter is the ISO. So this basically adds brightness, but it also increases noise, very much like this example that you're seeing over here. With all of that, when we are measuring materials, we need to understand the depth of field, especially if something is moving in and out of focus. Depth of field becomes quite an important factor. And again, depth of field is determined by the aperture, whose size also determines how much light is coming in, which then also determines your shutter speed. So there is a variability, there is a trade-off between all of these, and that's sort of something you can get over experience, or if not with a ton of calculations, right? So this is kind of an example of like having far focus with the depth of field as opposed to missing out on something that's going on nearby. And you can compute all of these with equations as well, as I said, but you know, from my practical experience, I feel that doing it by hand and actually using the system helps you a lot more just to intrinsically understand what's going on with the camera system, as opposed to using the equations for actually physically taking the image. Now, most cameras are again based on the pinhole camera model, which is a very simple camera model, basically stating that a point at a certain object distance, if the rays of light pass through this convex lens, it would then pass through the focal length or through the optical center or parallel to the optical axis, and eventually land on the sensor plane, which is then determined as the image distance. And that is also determined by this equation, which is known as the lens makers equation. So now that you have like sort of a broad perspective on the fundamentals, let us break into the image processing techniques. Now, most image processing techniques generally utilize something called a convolutional kernel. Now, imagine this is your image, right? So each one of these tiny square boxes is a pixel with a certain intensity ratio or a grayscale value. Now, when I perform image processing, essentially what I'm doing is I'm sending a smaller subset of pixels or a kernel such as this across the entire image so it can extract some properties. And that is basically used for image processing techniques such as edge detection, match filtering, or blurring. So in essence, I take that convolutional kernel, and then I pass that across my entire image as it goes across. And based on the results from that, I can then derive properties of the image itself. One of those examples is the Laplacian second derivative edge detection. So if you see this image that is given over here, which is fairly standard, like black, white, black, which is what is represented with this matrix over here. So 0 stands for black, 1 stands for white. If I run that with the convolution of this 141, 4 minus 24, 141, what I can extract is this edge detection, which gives me where the edges are between those planes. And using that, then I can identify a lot more characteristics of the image as opposed to just seeing the color itself. Some of the examples of using edge detection is, say if this is the original and you have a blurred image, you can also create an edge enhanced. So you can see how edge detection is basically used over here. Or you can just pull out only the edges themselves, right? Now, from the edges, we can also extract gradient values. Basically, that determines how much your image intensity changes from light to dark or from dark to light. So this is basically an X gradient. So it's checking how much image intensity changes horizontally. And then there's also the Y gradient, which shows the same aspect, but vertically. And then you can square and sum the both of those to get the magnitude of the gradient, which will give you a little more features of the object itself. So these are different ways that simple image processing tools, we're basically running a tiny matrix across the entire image to extract these high quality resolution data points, which we can then use for computer vision for actual intelligent decision making based on those images. There are some more further slightly more complex image processing techniques such as dilation. Dilation is, again, it's as it says, it basically dilates the object. Erosion erodes the object. Opening is basically a process of eroding, so basically cuts down some part of the image and then dilates it. And closing is the other way around. Now you can see some of these aspects kick back in. So over here you're seeing an example of dilation. So basically that object has been dilated. Another example that you're going to see over here is opening. So basically what this feature does is it removes these smaller image parts. So essentially something that's not as thick, right? So if it's only like 1 or 2 pixels wide, the opening is going to first erode it. And then once it's eroded, then it's going to dilate everything else. So you get to you lose out on these random artifacts that's in your image. Same kind of idea for closing. So it's going to dilate the image. So basically you see this little gap. It's going to extend the white regions around there. And then it's going to erode the edges again. So you get back into that standard shape function, right? And again, this is done across every pixel or based on different properties. Now, using all of these, we can then use this information from image processing for slightly more complex algorithms such as segmentation, right? So we're basically breaking the image into pieces based on color, location, or gradient, and then assessing properties of that. Now, one reason segmentation is useful, especially computationally, outside of a human just eyeballing it, is it's a classic example of, hey, do you think the color of cell block A and the color of cell block B are the same? And for me, with my naked eye, it obviously looks different. Like B definitely looks lighter than A. But in fact, when you pull out the data, they are the same grayscale value. It is just an artifact of how our mind perceives this. Now, sometimes that might be useful, but most times we want to get, we want to get the true value results from the image segmentation process, and therefore like using image processing and computer vision is massively useful. One of the examples of using segmentation is, say we are trying to identify points on the structure, right? So we're going to segment this image by thresholding all the yellow parts, then doing a shape assessment on the circulars versus the squares, and then finding out the size, and if required, we can do some clustering algorithms as well. Same thing we can do for identifying cracks within a wall. We do some segmentation, we do some shape analysis, and then we do some clustering, and then subsequently at some point some filtering to identify the cracks within the system itself. On a more micro scale, we can use image segmentation for grain segmentation. So basically your the grain values within the microstructure of your metal, for example. So we can identify where the grain values end, where the grain values start, and figure out why the hardness is different between two different points within the same matrix. Again, another example is histogram equalization, and you can see different varieties of histogram equalization. If this original image using a global method, you would get an image such as this, which has its own viable properties which can be used, but a little more useful for the user would be an adaptive thresholding methodology, such as this one given over here. A little more complex look into image processing, and I'm just going to mention this for the sake of covering it, is using fast Fourier transforms, which help us identify repetitive features within the structure itself. Most of this is predominantly used within the signal processing aspect of it, but this is probably something that you should know about within your curriculum if you're covering image processing as well. With that, we're finally going to move into measurements. Now, generally for measuring with an image system, you need to have a reference and a deform stage. Now, images generally don't have physical units, so we need to find a way to take a picture where we can convert those pixel values of the picture into actual measurable distance. Now, when doing that, problems such as lens distortion, which you're seeing over here, which is also known as the fisheye effect or the fishbowl effect, comes into play. So we need to find a way to correct for that, doing certain forms of camera calibration, which can then give us a corrected form of the image, where then each pixel represents an equal length, right? So as you can see over here. Now this requires like 5 to 10 images of a calibration panel, but that's a little more detail than you actually need to go into. I just want to let you know that correcting the fisheye lens is a requirement, especially when using images for physical measurements. Another one is sometimes when you're taking images, you might not be able to take them at the angle that you require. And times like this, you don't have to worry about these equations. This is just because it was available, we put it in there. It's called homography, where we can project these images into a different plane. So say I take this image of like the Drexel's main building, right? Taken from Chestnut Street. If we turn that around, saying I need all 4 points of this building to be the same image length, I can then use that along with homography to then realign my image. And now I can do some standardized image processing or like computer vision on this image, which has been corrected for that vision, right? And that's some of the higher end image processing methodologies that you can use. Going a little bit further into high-end image processing algorithms, one of them is optical flow. And this is basically a simple form of digital image correlation. And we're going to break into that a little bit. But we basically use image stitching and light intensities within the same field of view as it changes to identify motion in the image itself, right? So say I have this example. So you can see these gears turning, And using optical flow, then I can identify by how much these gears are turning, right? So we are basically calculating motion of gears based on a calibrated camera's images. A little more advanced version of this optical flow is something called digital image correlation, which can be within 2D, which is basically saying how much something moves in the X and Y plane, or 3D, which tells you how much something moves in the XYZ plane. And this essentially works by correlating an image with, well, an undeformed image with a deformed image to identify how much it has actually shifted, right? And based on that correlation, we can then extract motion values. There are commercial aspects of this system. So as you can see, there are test dummies which use digital image correlation, which is essentially optical flow to tell you how much motion there is within the crash test dummy. This is an example of a rubber bullet shooting a helmet, and you can see how much internal displacement there is. And from that, you can identify if there's going to be brain damage. There are some examples of light bulbs breaking and of like a chip that's expanding as well, right? So now these are the various tools that you can use. However, in your lecture today or in your homework today, we are going to be breaking you down through a handful of tools that might be useful. Personally, I think it's a lot of fun, at least like the homeworks that we were able to create for you guys. It's more of a trial and error and like using some common sense and a little bit of Googling. But some of the common, well, functions that you'll be using within MATLAB for this homework assignment would be your RGB to gray. So basically converting your 3-colored image, so your red, green, blue image to like a grayscale value, using a image Gaussian filter to help you analyze, and you're going to see what that does. You can use the IM binarize to convert an image to black and white. You can do a black and white perimeter to identify just the perimeter of the structures itself. And using that, you can also use a function called region props, which for all intents and purposes analyzes a black and white image and then can get you statistics. Some of the common tools we're going to be using predominantly would be the color thresholder, while we walk through the blob detection and the all frames. And then we will walk you through your homework as well. Now, the color thresholder has a page such as this, which will be useful, where you select which image space, which color space you're going to be playing with or like thresholding with, and then extract data from there. Another one that you'll be using is Strel, which is basically a structural element that you can use to extract or open up specific shapes within your image. And well, we're going to be running a blob analysis, which I think should be exciting for you guys just to do it on your own, to identify and count how many blobs are there within a moving video frame. All right, with that, I'm going to thank you for your time. And if you do have any questions, please do direct them to Dr. Consos, or feel free to email me at mdm, that's Mike Delta Mike 359 at drexel.edu. With that, thank you and stop my video recording. Hope this was useful, and I guess I'll see you in the homework video tutorial. All right, bye-bye.